Dinosaurs that inhabited the Korean peninsula were mainly present during the Cretaceous period. The Cretaceous period, spanning from approximately 140 million to 66 million years ago, marked the heyday and extinction period of dinosaurs. During this time, the Korean peninsula, which was connected to China and Japan as a single landmass in the Mesozoic era, experienced significant tectonic movements, leading to the formation of large lakes during the Jurassic period. The mild climate of the Korean peninsula and the abundant vegetation and prey around the lakes created an ideal environment for dinosaurs to thrive. Fossils of dinosaurs discovered in the region include bones, eggs, and footprints. Bone fossils provide insights into the types and forms of dinosaurs, while footprint fossils offer information about their behavior and ecology. Notable dinosaur species found in the Korean peninsula include Protoceratops, Tarbosaurus, Velociraptor, and Therizinosaurus. Among these, Protoceratops was an early herbivorous dinosaur with a horn. Tarbosaurus resembled a carnivorous dinosaur similar to Tyrannosaurus rex. Velociraptor was a small and swift carnivorous dinosaur, and Therizinosaurus was a herbivorous dinosaur with long claws. The distribution of dinosaur fossils in the Korean peninsula is mainly concentrated in Gyeongsangnam-do and Jeollanam-do. Goseong in Gyeongsangnam-do is renowned as one of the world's top 3 dinosaur footprint fossil sites, with over 1,800 dinosaur footprints discovered. Additionally, Haekyong in Jeollanam-do is home to the world's largest collection of dinosaur footprints. Furthermore, Haedong in Gyeongsangnam-do has well-preserved dinosaur bone fossils that have been internationally recognized. The dinosaurs that once roamed the Korean peninsula represent a valuable heritage that provides insights into the past history of life. Preserving and studying dinosaur fossils will contribute to elevating the level of dinosaur research in our country. Moreover, exploring dinosaur fossils allows us to learn about the appearance, characteristics, lifestyle, behavior, and environmental changes of dinosaurs in an engaging and interesting manner. I will provide information about pterosaurs in the Korean peninsula. Pterosaurs were flying reptiles that coexisted with dinosaurs. Unlike dinosaurs, pterosaurs belonged to a different group of reptiles, and their distinctive feature was the presence of wings. They primarily inhabited areas near water bodies or lakes and fed on small animals, insects, and fish. In the Korean peninsula, numerous pterosaur footprint fossils have been discovered. In Haekyong, Jeollanam-do, the world's largest pterosaur footprint was found, measuring 55 centimeters in length and 50 centimeters in width. This pterosaur is estimated to have been a large species, approximately 5 meters in length. Additionally, in Chinju, Gyeongsangnam-do, in the Jeongkon area, thousands of pterosaur footprints dating back to the Cretaceous period, around 100 million years ago, were uncovered. These footprints provide valuable insights into the diverse behaviors and ecology of pterosaurs. Pterosaurs in the Korean peninsula play a crucial role in understanding the natural history of our country alongside dinosaurs. It is essential to preserve and study pterosaur fossils to gain a better understanding of their lives and appearances. I will provide information about the glaciation that occurred on Earth and the Korean peninsula. Glaciation refers to a period when the Earth's climate becomes significantly colder, leading to the freezing of continents or oceans. Throughout Earth's history, there have been several glaciations, with the most recent and extensive one known as the last glacial maximum, LGM, lasting from about 24,000 to 12,000 years ago. During this period, the Earth's average temperature was approximately 6 degrees Celsius lower than today, and massive ice sheets formed, covering more than half of the continents, particularly concentrated around the polar regions. The Korean peninsula was also influenced by the last glacial maximum. The average temperature in the region was about 10 degrees Celsius lower than present, and the sea level was approximately 120 meters lower. The northern and eastern parts of the Korean peninsula were covered by ice, while the southern and western regions featured expansive steppes and tundras. Plant and animal life in the Korean peninsula adapted to the cold, and human populations adjusted their lifestyles to the glacial environment. Natural factors, such as variations in Earth's orbital and axial parameters, changes in solar activity, and volcanic eruptions, as well as human activities like the emission of greenhouse gases, industrialization, and deforestation, play crucial roles in determining glaciation. These factors interact in complex ways, influencing climate changes and the onset and conclusion of glaciation periods. Glaciations have significant impacts on Earth's ecosystems and environments. During glaciations, temperatures drop, ice sheets expand, sea levels decrease, biodiversity decreases, and human civilizations undergo transformations. As glaciations end, temperatures rise, ice sheets retreat, sea levels rise, biodiversity increases, and human civilizations advance. Understanding the patterns of glaciation helps provide insights into Earth's past, present, and future. I provided a brief explanation about glaciations on Earth and the Korean peninsula. If the Earth's axial tilt were vertical, significant changes would occur in the planet's climate and ecosystems. If the Earth's axis were vertical, there would be no seasonal variations. Currently, Earth's axial tilt results in different angles at which sunlight reaches the planet during its orbit around the Sun, causing seasonal changes. However, if the axis were vertical, sunlight would fall at a consistent angle every day, leading to constant temperatures and day and night lengths throughout the year. A vertical axis would alter the temperature distribution and climate on Earth. Near the equator, where sunlight is always concentrated, it would be consistently hotter and drier. Conversely, polar regions, receiving minimal sunlight, would become even colder. This temperature disparity would affect wind and ocean currents, disrupting Earth's energy circulation and creating climatic instability, posing challenges for the adaptation and evolution of living organisms. Moreover, with a vertical axis, the movement of the Sun and Moon would change. Earth's axial tilt currently causes seasonal variations, lunar and solar positions, and phenomena like solstices and equinoxes. If the axis were vertical, these phenomena would cease to occur. The movement of the Sun and Moon influences gravitational forces, affecting tides and Earth's rotation and revolution speeds. While it's highly improbable for Earth's axis to become perfectly vertical, exploring such hypothetical scenarios allows for scientific inquiry into potential consequences for climate and ecosystems. If Earth's axis were horizontal, the climate and ecosystems on Earth would undergo even more drastic changes. With a horizontal axis, the regions near the equator would consistently receive intense sunlight at a steep angle, resulting in extremely hot and dry conditions. In contrast, polar regions would consistently receive sunlight at a low angle, leading to extremely cold temperatures. This temperature difference would intensify wind and ocean currents, destabilizing Earth's energy circulation. Such conditions would make Earth's climate extreme, posing challenges for the adaptation and evolution of living organisms. Furthermore, with a horizontal axis, seasonal changes would become highly pronounced. Currently, Earth's axial tilt causes variations in the angle at which sunlight reaches different parts of the planet during its orbit around the Sun, contributing to seasonal changes. If Earth's axis were horizontal, seasonal variations would be extremely extreme, with regions experiencing consistently high or low temperatures and day and night lengths throughout the year. A horizontal axis would also complicate the movement of the Sun and Moon. Earth's axial tilt currently causes phenomena such as eclipses, solstices, equinoxes, and the changing positions of the Sun and Moon during the year. With a horizontal axis, these phenomena would be diverse and irregular. The movement of the Sun and Moon influences gravitational forces, affecting tides, as well as the speed and period of Earth's rotation and revolution. While it is highly unlikely for Earth's axis to become perfectly horizontal, exploring such hypothetical scenarios allows for scientific investigation into potential consequences for climate and ecosystems. If Earth's axis were at a 45-degree angle, the expected changes would be even more severe. If Earth's axial tilt were to become 45 degrees, the seasonal changes would become extremely pronounced. With a 45-degree axial tilt, as Earth orbits the Sun throughout the year, the direct sunlight from the Sun would strike the planet at vastly different angles. This variation in angles is closely related to the changes in seasons. If Earth's axial tilt were 45 degrees, the seasonal variations would be extremely extreme, with regions experiencing consistently high or low temperatures and day and night lengths throughout the entire year. Moreover, with a 45-degree axial tilt, the motion of the Sun and Moon would become highly complex. If Earth's axial tilt were 45 degrees, the planet would experience a diverse and irregular array of phenomena such as solar and lunar eclipses, the rising and setting of the Moon, and the movement of celestial points throughout the year. The motion of the Sun and Moon influences gravitational forces, impacting tides, as well as the speed and period of Earth's rotation and revolution. Therefore, if Earth's axial tilt were 45 degrees, the speed and duration of Earth's rotation and revolution could become highly variable. If Earth's axial tilt were set at 45 degrees, it can be anticipated that the climate and ecosystems on Earth would undergo extremely severe changes. While the likelihood of such a scenario occurring in reality is very low, exploring these hypothetical situations allows for scientific investigation into potential consequences for climate and ecosystems.